Welcome to our exploration of the Quicksort algorithm, a sorting technique renowned for its efficiency and practicality in diverse computational contexts. Despite its worst-case running time of theta of n squared, which occurs in highly unbalanced partitioning scenarios, Quicksort is widely preferred due to its average case performance of theta of n log n. This efficiency is achieved through its divide and conquer methodology and the small constant factors hidden in its time complexity. What sets Quicksort apart is its in-place sorting capability, making it memory efficient compared to alternatives like merge sort, which require additional storage. It also excels in handling large datasets, even in environments with limited memory, such as virtual memory systems. Over the course of this presentation, we will delve into the inner workings of Quicksort, examining its algorithmic structure, key features, and performance analysis to understand why it remains a cornerstone of modern computing. Quicksort's effectiveness stems from its foundational features, each contributing to its status as a go-to sorting algorithm. First, it employs a divide and conquer strategy, systematically breaking down a complex problem into simpler subproblems. This approach not only enhances its computational efficiency but also aligns well with recursive implementations, making the algorithm elegant and intuitive. Second, Quicksort sorts arrays in place, requiring minimal auxiliary space. This feature is crucial for applications where memory resources are constrained. Moreover, Quicksort thrives on large datasets, particularly in virtual memory environments where minimizing input-output operations is critical. Its adaptability is another hallmark. Various optimizations, such as randomized pivot selection and hybrid approaches using insertion sort for small subarrays, can significantly boost its performance. These features collectively make Quicksort an indispensable tool in both theoretical studies and practical applications. The Quicksort algorithm unfolds in three main phases: divide, conquer, and combine, each playing a pivotal role in its functionality. In the divide phase, the array is partitioned around a pivot element. This operation splits the array into two subarrays. Elements smaller than or equal to the pivot form the left subarray, while elements greater than the pivot form the right subarray. The pivotal element is then positioned in its correct, sorted location within the array. During the conquer phase, Quicksort recursively applies the same logic to both subarrays, ensuring that each is sorted independently. Finally, the combine phase is implicit. Since the subarrays are already sorted, no additional work is required to merge them. This three-step process underpins Quicksort's efficiency and scalability, allowing it to handle arrays of varying sizes and characteristics effectively. Its recursive nature ensures that even complex datasets can be sorted with minimal computational overhead. The formal implementation of Quicksort is captured in the Quicksort procedure, which integrates recursion with the partitioning process. The algorithm begins by checking if the subarray contains more than one element. If this condition is met, it invokes the partition function to segregate the array into two parts based on a pivot element. This pivotal index determines the boundaries for subsequent recursive calls to sort the left and right subarrays. By recursively calling Quicksort on progressively smaller subarrays, the algorithm achieves full sorting. To sort an entire array of size n, the process is initiated with Quicksort of a1, n. This recursive breakdown continues until each subarray reaches the base case of containing a single element or no elements, at which point the recursion terminates. The elegance of Quicksort lies in its simplicity and the efficiency of its divide and conquer methodology. The partition procedure is the cornerstone of Quicksort, serving as the mechanism that enables efficient partitioning of the array into manageable sections. This function selects the last element of the subarray as the pivot and rearranges the other elements so that those smaller than or equal to the pivot are placed to its left, while those larger are moved to its right. The pivot is then positioned in its correct sorted location, effectively dividing the array into two segments for recursive processing. The function returns the pivot's index, facilitating the recursive calls that follow. The quality of partitioning directly impacts Quicksort's performance. A balanced partitioning, where the two resulting subarrays are of approximately equal size, leads to an average case running time of theta of n log n. In contrast, highly unbalanced partitioning can degrade performance to theta of n squared. Thus, the efficiency of the partition step is pivotal in determining the algorithm's overall effectiveness and reliability. The partitioning process is a critical component of Quicksort, as it dictates how the array is divided into smaller subarrays for further processing. First, the algorithm selects a pivot element, which is typically the last element of the subarray. Next, it rearranges the elements such that those less than or equal to the pivot are placed to its left, and those greater than the pivot are positioned to its right. Finally, the pivot itself is placed in its correct sorted position within the array, ensuring that it separates the lower and upper partitions. The efficiency of the partitioning process directly impacts the overall performance of Quicksort. A balanced partitioning leads to optimal recursive divisions, while unbalanced partitioning can degrade performance. Understanding and optimizing this step is essential to fully harness the potential of Quicksort. Quicksort's performance varies depending on how well the partitioning divides the array. In the best case scenario, the partitioning produces balanced subarrays of roughly equal size, leading to a running time of O of n log n. The average case performance, when all permutations of input are equally likely, is also O of n log n, making it suitable for most practical applications. However, in the worst case scenario, such as when the pivot results in highly unbalanced partitions, the running time deteriorates to theta of n squared. This variability underscores the importance of good pivot selection strategies and techniques, such as randomization, to improve the likelihood of balanced partitioning. By mitigating worst-case scenarios, Quicksort achieves its renowned efficiency and robustness. Randomized Quicksort is a variation designed to overcome the limitations of traditional Quicksort by reducing the probability of encountering worst-case scenarios. Instead of always selecting the last element as the pivot, this approach chooses a random element from the subarray. The chosen element is then swapped with the last element before the partitioning process begins. This randomness improves the likelihood of balanced partitions, even for inputs with specific patterns that might otherwise cause highly unbalanced splits. The expected running time of randomized Quicksort is O of n log n for all inputs, making it an effective and practical solution for a wide range of sorting problems. By incorporating randomization, this variation enhances both the efficiency and reliability of the algorithm. The randomized partition procedure is a key component of randomized Quicksort, introducing randomness into the pivot selection process. The procedure begins by selecting a random index from the subarray. This element is swapped with the last element, which becomes the pivot for the partitioning process. The algorithm then proceeds with the standard partition logic to divide the array into two subarrays based on the pivot. By ensuring that each element has an equal probability of being selected as the pivot, randomized partition reduces the chances of encountering highly unbalanced partitions. This randomness is the foundation of randomized Quicksort's efficiency, as it helps achieve balanced splits on average and avoids the deterministic worst-case behavior of the standard approach. Randomized Quicksort is an enhanced version of the standard Quicksort algorithm, leveraging the benefits of randomization to achieve consistently good performance. The procedure closely mirrors the original Quicksort logic, with the key difference being the use of randomized partition instead of the standard partition. By incorporating random pivot selection, randomized Quicksort ensures that the likelihood of balanced partitions remains high across all input types. This randomized approach is particularly effective in scenarios where the input may exhibit patterns that lead to worst-case behavior in standard Quicksort. With an expected running time of O of n log n, randomized Quicksort provides a robust and versatile solution for efficient sorting. The analysis of Quicksort provides insights into its behavior across various scenarios, from worst case to average case performance. In the worst case scenario, partitioning is maximally unbalanced, resulting in one subarray containing all elements except the pivot. This leads to a running time of theta of n squared, which occurs when the input array is already sorted or reverse sorted, and the pivot selection is poorly chosen. In the best case scenario, partitioning is perfectly balanced, with each subarray being of equal size, yielding a running time of omega of n log n. The average case performance, however, is more reflective of Quicksort's true efficiency. Randomized pivot selection ensures that most partitioning splits are reasonably balanced, leading to an expected running time of O of n log n. This makes Quicksort a practical choice for a wide range of applications. Understanding Quicksort's expected running time involves analyzing the number of comparisons made between elements during its execution. Two elements are compared if and only if one of them is chosen as a pivot before any other element between them. The probability of such a comparison depends on the relative positions of the two elements within the array. For elements z_i and z_j, where I is less than j, the probability of comparison is 2 divided by the quantity j minus I plus 1. By summing the probabilities across all pairs of elements, we find that the expected number of comparisons is O of n log n. This analysis highlights the efficiency of randomized Quicksort, as it achieves balanced partitioning on average and minimizes unnecessary comparisons. Quicksort can be further optimized to enhance its performance, especially in practical implementations. One common optimization is to use insertion sort for small subarrays below a certain size threshold, as the overhead of recursive calls becomes less efficient for small datasets. Another technique is the median of 3 pivot selection, which chooses the median of the first, middle, and last elements as the pivot. This improves partitioning balance and reduces the likelihood of encountering worst-case scenarios. Additional optimizations include three-way partitioning, which efficiently handles arrays with many duplicate elements, and tail recursion elimination, which reduces stack space usage. These refinements make Quicksort even more adaptable and effective in real-world applications. When comparing Quicksort to other sorting algorithms, its strengths and weaknesses become apparent. Quicksort has an average case running time of O of n log n, similar to merge sort and heap sort. However, its worst case running time of theta of n squared is less favorable than the guaranteed O of n log n worst case performance of merge sort and heap sort. In terms of space complexity, Quicksort is more efficient, requiring only O of log n additional space, while merge sort requires O of n. Quicksort is not a stable sorting algorithm, meaning it does not preserve the relative order of equal elements. Merge sort, in contrast, is stable, making it a better choice for applications where stability is critical. Despite these trade-offs, Quicksort's adaptability and speed make it a preferred choice in many scenarios. In conclusion, Quicksort remains one of the most efficient and widely used sorting algorithms due to its average case performance and versatility. Its divide and conquer strategy, in-place sorting capability, and adaptability to optimizations ensure that it performs well across diverse datasets and environments. Randomized versions of Quicksort further enhance its reliability, mitigating the impact of worst-case scenarios. Moreover, Quicksort has become a fundamental example in algorithmic analysis, offering insights into recursion, partitioning strategies, and the balance between theoretical performance and practical efficiency. Ultimately, Quicksort's enduring popularity stems from its ability to balance simplicity, efficiency, and adaptability, making it an essential tool in both academic and real-world computing contexts.